So to continue, when you get to actually before you get to visit your client, it would be good to have them get at least 1 year of electrical bills. 2 years is even better, and they can be downloaded in many cases in the form of a spreadsheet, which makes it very easy to move around. The reason we want to do this is we want to look for trends. We want to see if there's areas where we can reduce the client's loads. Remember, by having a smaller load, we end up requiring less energy creation equipment, meaning a smaller turbine, a shorter tower, and so forth, which is going to save them, the customer, money. So we'll save them money by reducing their electrical load, and we'll save them even more money by putting in a smaller system to take care of their needs. And we'll also want to go and identify the primary loads in the home. What are the energy using components? So here's what my electrical bill looks like. I have We Energies, and you'll notice that this spreadsheet, I've imported this into it, and there were 4 different versions that I could bring in. One was called an account summary, which is really clear. It just says what the billing dates were from and to, right? How many kilowatt hours were used based on subtracting the meter charge this last month from the meters reading this month. So we can see really simply just how much my energy charge was. So in February to March was 629 kilowatt hours this year. Compare that to last year, 778. Okay, so it cost me, there was a lot more energy being used. Was it colder last year, or were we just more frugal? Hard to say. So this is one way that we can do this. Another tab that they have is to bring in that shows the meter number, again the billing date, the number of billing hours used. Now here we're going to see the charge for the electricity, and then we're going to see the facilities charges. So those are things like taxes and help for people who are having trouble with their bills, and other surcharges and so forth, but mostly it's the benefit of having a meter hanging on the wall. So this is how this breaks down. Again, we can see this was just another tab that I combined all together in one spreadsheet. Well, if I go even further then, if I break the facilities charges down even further, I can see exactly what happened here. Now, some of you may remember last year in the state of Wisconsin that the Public Service Commission asked for a rate change. And they got it. And their complaint was that all these renewable energy people weren't paying for their fair share of electricity. And so they wanted to increase the fixed charge and slightly decrease the electricity charge. And so that's what they asked, and that's exactly what they got. So just let me show you this. I'm going to zoom back in a little bit, make it a little bigger, 125%, right? So we're going to see this, right? So we can see when this took place, right? This took place, it took place fully. It started in December and January, and you can see the rate started to go up a little bit here. We were hovering around $9 for our fixed charge, right? And then in January and February it went up to $15.48. It's gotten as high as $18.41. It's roughly $16.50 is what it averages out to be. The fuel cost adjustment we can see has always been plugged in here, and then so we can see that most people, their facilities charges doubled. So what ended up happening to my electric bill, right? So from February to March, my electric bill went from $102, $119.46, and it dropped to $101.79. So one of the issues with this is, if we look back one tab, remember, I used less energy. I'm comparing 778 kilowatt hours to 629 kilowatt hours. So what this does is it removes the incentive for people to use less energy. You don't get penalized for using energy, so that can be an issue. So I'm going to get off my soapbox there, and I'm going to come back over here, and this is the last one that I did. I kind of put everything together here, and we can see, not only can we see the number of kilowatt hours that were used. Again, I just moved Excel around a little bit here. I made some totals and averages. This is an average, right? So if I click here, it's going to tell me this is the average of F5 through F16. So that's in a whole year's worth, right? And we can see the number of kilowatt hours. So my average kilowatt hour per day was 21.02. So you can see I got down into the teens. Well, why would that be? Why would it be that my kilowatt hour usage has gone down? Because I'm implementing some energy conservation steps, and because it was warmer. Notice we've got the heating degree days and the cooling degree days. I'm going to scroll down, and I've got the totals highlighted here, right? So the 1 year period ending in March of this year, the heating degree days were 548. Okay, what that means is I had to use the heat less this year than I did last year. Woo. Well, I'm only comparing a year's data. This certainly does not prove that climate change is happening, but the trend, if we go back, if I could get this data from We Energies for the 10 years that I've been there, I would be able to actually track that information. And a 10-year history is, although we're still tracking data there, we're not tracking climate. You know, it's not climate data, it's more weather data. But still, I find it telling. So, and then notice the cooling degree days. Look at that. Cooling degree days went from 34 cooling degree days the year before to 47 cooling degree days. So this is some of the information that we're going to need for for a report. Our report looks like this. Okay, this is the full report right here. The client information goes in here. The assessor has a spot to put in his name, company address, and contact information. If you have a site assessor certificate number, it goes there. Here's the table of contents, which we will correct. We will add the appropriate page numbers. We'll have the address in here, and we'll answer these questions. Why are they interested in renewable energy, and so forth. The load analysis, how many people are in the household, and what is the monthly consumption? Monthly consumption, there we go. Mine averaged out over the last year to be 643. The year before, 718. It might be fair just to average the two together and call it, I don't know, 680? 680. That would be a good estimate to put here. What is the current electricity rates? Well, I could put down that it's so many cents per kilowatt hour. How could we calculate that? Well, divide the number of kilowatt hours by the electricity charges, and it'll tell me exactly how many kilowatt hours, how many cents I was paying per kilowatt hour. So I could do that. And then also the annual consumption. Any load considerations to consider here? Plan on getting some fish, getting rid of the fish tanks, installing a greenhouse. You know, so there could be a variety of things that I might want to list here. And this is the table where we're going to fill in the information that we just showed you from the bill. When we talk about energy efficiency and load reduction recommendations, one moment, we're going to go back to the presentation, right? And we'll come back to that template here in just a moment. So if you don't have any usage history, you can go back to the former home. Again, you can compare square footage. You can compare the occupancy. At the old home, both kids were there. At the new home, one child moved on. He got married on there, or he's off to college or whatever. What's the load profile about? Now, this is where we literally go through the home, room by room, fixture by fixture, and we ask questions like, how often do you keep these lights on? Are these lights on 4 hours a night? Are these lights on every day? Are they on the weekend? Do you leave your computer on all the time? How often is the TV on? Literally every fixture, every device that plugs in, we're going to want to get an idea of how often it's on. Maybe in the summertime you don't watch as much television. Okay? So maybe that would explain why your electric bill is lower. Here we go. So here is June, right? In June, I used 26 kilowatt hours per day, whereas in July, I used 23. Well, what about last year? What did we do? All right, so June happens to be 16. It was 16 month, all right? So we're going to see some lower trends. So it looks like the energy is being used in my home. What in the world was going on in September and August and September of last year? 1,036. What happened? Well, I know one of the things that happened. I had a dehumidifier that turned on and didn't shut off. And it was continuing to run. That's like leaving a compressor on the whole time. So that was an amazing amount. It was also a fairly warm summer, which meant the air conditioning was on, which is yet another compressor. So those are things that you can try and find there. We will also use a kilowatt meter. We're going to see a picture of one of those here in just a moment, so we can determine what the energy use is on the individual devices. Light bulbs are pretty simple to look at. We can look at the side of them, and especially if it's incandescent, we can find out how many watts it uses. Otherwise, we can use the kilowatt meter, or we can use the packaging that the bulb came from, or estimates that are on some of the labeling. Again, I'm going to show you what a kilowatt meter looks like here momentarily. Now, as far as interviewing the client, again, I've talked to some of these things. Kids going off to college, done with college, coming back home. Are we planning on replacing any appliances or systems? How old is the furnace? Oh, it's 15 years old. Might be time for a new one. It's a good opportunity to get one that's far more energy efficient. Same thing, the refrigerator, the stove is an electric stove. Is it a gas stove? Will you be doing any other things, like, for example, starting a home office or some sort of a workshop or a business that's going to be using more electricity? Maybe you'll be shutting some down. Maybe you'll be shutting down the wood shop, and so on and so forth. So these are the kinds of questions you would ask the client. You will likely be surprised with what you find out. So this is an example of one of the kilowatt meters that's available. This is called the Kilowatt EZ. You can get these anywhere from $20 to $40. And they will show you how much energy is being used. You can see there's a menu. We can scroll up and we can scroll down. We can reset it, and we can also make some settings. So this particular one is a little more complicated than the S3 model. The S3 model is very simple. And these buttons, instead of having a menu, you can literally pick one for volts, another one for amps, another one for watts, one for kilowatt hours, and one for power factor. And so they some have two functions. Sometimes I think this has more buttons than you need, but it's very effective as well. So what do we plug in? The kinds of things that use a lot of energy. This would be a window air conditioner, because it has to plug in here. It has to plug into a standard 120 volt outlet. Same thing with space heaters or water heaters. I already mentioned to you the problem I had with the dehumidifier. Refrigerators and freezers. I think some of you have heard about the beer refrigerator story. If you buy a new energy efficient refrigerator and are so happy that you did and justified buying it because you'd get rid of that energy inefficient one, and so now you've saved all that money, but didn't get rid of the old refrigerator, instead put it in the garage and left it plugged in, so now you're cooling nothing and spending money for it. Incandescent lighting, of course, uses a lot of energy, so we can see exactly what's going to use the energy using a meter that's similar to this. There are other devices that are out there. This is by far the easiest and most popular that you're going to find. So again, here's the template. We've already looked at this a little bit. And the energy efficiency recommendations. This is based on your walkthrough. You can talk to the client, and you can mention to them this very quote. Notice it's in quotes. You want to tell them every $3 to $5, every dollar I spend on efficiency, you're using $3 to $5 from the cost of the renewable energy system. Efficiency, of course, that means doing the same with less. So if I was lighting a garage with a 100-watt light bulb that was on the whole time and only putting out a certain number of lumens, I could maybe get even more light out for half or even a third of the amount of energy that was being used. So efficiency is really important. And by being able to show them that by reducing their consumption, they can start saving money right now that could be going towards the wind turbine or whatever they decide to put in. We're going to talk about phantom loads here in just a moment. I've got a slide coming up. Phantom load, these are things that have the small transformers, like your cell phone charger or your or maybe an answering machine or your computer. So it plugs into the wall, and then yet there's another plug that comes out of it to plug into that particular device. And so that's what's known as a phantom load. And part of these recommendations will be done just to literally educate the consumer and to help them make better, more cost-saving and energy-saving decisions. So ways that we can do this. We can give them the specific numbers, right? So here, we can get these examples of energy efficiency, and here's a couple of websites where we can go look, applianceinformation.com, so we can look up by date codes how much energy a device is supposed to use. There's a good chance the device that you have in your home will be on this list. Maybe the part number will be off by a digit or two for color, or some other option that yours doesn't have, but the basic guts of the machine should still be there. Same at EnergyStart.gov. So in this example, if the current refrigerator uses 300 kilowatt hours per month and a new one only uses 50 kilowatt hours per month, and those numbers are not outrageous, that's a very doable thing. So I'm going to save 250 kilowatt hours per month, and because the thing is cycling a certain number of times per day, it can be calculated out to run, so that would be 3,000 kilowatt hours per year. When we multiply that times 10 cents per kilowatt hour, that comes up to $300 a year. Okay, so that being the case, the refrigerator is probably going to last at least 10 years before it needs any sort of work whatsoever, right? And so if I divide the cost of the new refrigerator, $1,000, by the amount of energy, the amount of money I'm going to save each year, I'll see that that refrigerator is paid off in 3.3 years. Every year after that, before I have to do any repairs on it, I'll be just like saving an extra $300 a year. What can you do with that? Other tips: replace incandescents with LEDs or CFLs. Programmable thermostats are a very smart way to go, because we'll be, depending upon how you heat your home, you'll instead of just saving electricity, you may also be saving gas. There are things that you can do to the appliances in your home to make them run more efficiently. Water heaters don't have to get up to 150 degrees. You can actually have them only heat to 125 degrees, and they will do just fine and save you some money there. Most of you have probably heard already that the front-loading washing machines are more efficient. They're more efficient for several reasons. One, they use less water, which means you heat less water. If the water that you have in your home also has a water softener, then your water softener will have less wear and tear. Your salt use for your water softener will be less. So again, the front-loading dishwasher does that better. They also reduce the amount of water that's left in the clothes before you put them either in the dryer or out on the line. They're more gentle on your clothing, so your clothes last longer. They get cleaner. You use less water. You heat less of that water if you happen to be washing, so you win all the way around. Solar clothes dryers work very well once the temperature gets above 45 degrees. You can put them out on the line and dry your clothing that way. Instantaneous water heaters are very popular, and instead of keeping a huge tank of water heated, it's unnecessary. Other things, of course, get rid of the waterbed, and then finally, let's find a way to control the phantom loads. Again, we'll see that here in just a moment. So if we start thinking of the home as an entire system and start treating it that way, we can then lower our entire energy use and lower the amount of money that we're paying on this. Many local utilities have incentives for this, and those incentives would be to help people, for example, get a home energy audit done on your property, and that'll help you do things like insulate pipes, insulate hot water tanks, or even toilet tanks. Windows and doors, if they have leaky edges, leaky seams, that infiltration of air will tend to cause the conditioned air to leak out and the non-conditioned air to leak in. Insulation. So again, all of these things that we're seeing right here, every bit of these is cheaper than putting in a wind turbine or solar panels. Okay? These are the things we want to try to do before we put in those large systems, and if we need to educate the homeowner for this. I think we talked about load switching previously. You may be running some of your devices on purely electric right now because electricity is kind of cheap. Will it always be cheap? Or maybe you're running a lot of things on gas because right now gas is cheap. Will it always be cheap? The geothermal heating is kind of a misnomer. It's really a ground source heat pump here in this part of the country. So the ground source heat pump requires a lot of circulation and a lot of motors, which is a huge electrical load. So yes, you will be burning less gas, but your electricity bill will most certainly increase in proportion to the decreasing of the gas bill. And if you're not using geothermal, if you're just using an air-to-air heat pump, you will find that your electric bill goes up even higher. So I keep talking about phantom loads, and a phantom load is a device that is going to use power even though it's turned off. So if you're up in the middle of the night walking around the house, just look at all the little lights that are glowing at you. Little red light here, light on the microwave oven, the clock here, the clock there. Anything that's got a light on that's really not doing anything for you. I mean, do we really need the microwave oven to show that it's 2:45 in the morning if no one needs to look at it? Maybe they could design microwave ovens to only show those numbers when you press a button and when you want to look at it. So other things, cordless phone charging stations, cell phone chargers, computers, anything that's got the little wall wart or a cube that changes DC into AC. So this is an example of what those things look like. So here we see, wow, here's a kilowatt meter. Someone's measuring some of this, right? Here we got some cell phone chargers down here. There's a cell phone itself. This looks like some sort of I'm not even sure what that is. Here's a Macintosh iBook charger. Couple of, this is for a computer. Here we can see that there's the iPhone adapter. So these are all these things that if left on and not doing anything, it's just going to cost us money. Okay, so if you go to this website, cleantechna.com, there's a spot in the back of this chapter, the back of this module that has more information on this, good information. So we want to encourage people to get power strips. So if you don't want to plug things in and unplug them and plug them in and unplug them because you fear you'll wear out the socket or the wire or something, well, you can also then just turn off the power strip. There are some smart power strips out there that, for example, have 3 different style sockets. Maybe a socket up here towards the front is the sensing socket, right? So if I want this part turned off, if it shuts off, it would maybe shut off 2 other outlets. So this might be the stereo and the CD player and the DVD player. If the stereo's not on, I'm not going to use the CD player, the DVD player. So there's no sense in let those sit in there using energy. But then maybe I've got a couple other things down here that I don't want to have shut off. So there are some power strips that are smarter than others. Although these are the hardest things to change, our behaviors, they're also the free things, right? If I turn off a light when I'm not in the room, or the TV when I'm not watching it, or I hang my laundry out to dry. Or now there's some contention here as to washing dishes by hand is actually less expensive and uses less water than using a dishwasher. So that's one way to look at this. Another way to look at this is don't just let the water run. Okay, I know when my son comes home to visit and I hear him just turn the water on and it's on for 5 minutes straight while he's shaving, I could just throttle him. Okay, so that's not a smart way to do it. Turn the water on, turn the water off. It's not that hard. Same thing when you're brushing your teeth. You don't need to let that water run. Where I live, every drop of water has to be pumped out of the ground. And when it gets down into my basement, it has to be pumped into the septic system. So I'm pumping that water twice. Okay, other things. This is kind of counterintuitive. Full refrigerators and freezers do a better job when they're full than when they're empty. And the reason for that is the mass of the food that's in them, there's a greater thermal mass there. So once it gets cold, it's easier to stay held cold than would be a giant cube filled with air. Okay, so if you have multiple refrigerators and multiple freezers, some people, for example, we have more than one freezer. We raise our own animals, and when they're butchered, we need to fill the freezer. So sometimes of the year we have 3 freezers going, but as soon as we have the room to consolidate down to one, we normally do. It doesn't make sense to run a freezer that doesn't need to run. Okay, we've already talked about unplugging the phone charger from the wall. I'm going to go back a screen because I wanted to mention something here. When I look at a couple of these devices here, we can see this device here. There's a USB cord that plugs into the wart. Unplugging the USB cord from the wart doesn't make it shut off. There could be still a small drain. And if you're not sure, that's why I use the kilowatt meter. Oh, and then lastly, It's okay to wear a long sleeve shirt in the wintertime. Okay? And you don't have to, and in the summertime, it's okay to wear short sleeve stuff so that you don't have to have the house so darn cold. Okay? All right, now, so the template again, we looked at the template, we'll look at this again. So these are the same efficiency things that we had seen that we just went through here before. There's a few more that you can look at on your own. Same with heating and cooling, excuse me. And then, of course, we might want to think about time of use billing. Time of use billing we talked about before. It doesn't fit everybody, but it's worth discussing. If nobody's home all day long at all, and you come home and that's when you do your laundry and your dishes and your lights come on, maybe you could benefit by using a time of use metering system. All right, let's get down to some equipment. So we got the wind turbine out there in the middle of the field. And we got the wire running over to the service panel, and so now we need to figure out just how we're going to connect it up. So a couple things we need to know is there needs to be room. There needs to be room in the service panel. There needs to be in the room where the service panel is, if that's where we're going to install the rest of the equipment. Now, depending upon the turbine is going to determine which components are needed and how big that they will be. So you will have some sort of a controller or rectifier that's going to convert the energy coming down from the turbine into the proper type of voltage to get put onto the grid. That might mean a controller that actually just takes the AC that's being created by the turbine and puts it on the grid in a safe way. Or if you're getting three-phase wild AC, it needs to be converted into DC, and then that DC needs to be put into the inverter, which converts it back into the correct voltage and polarity and frequency of the grid. We have to be able to disconnect it. There will be a kilowatt meter that is required, or in some cases you'll need a second service meter. In the event that you have batteries, you will need a charge controller because we have to charge your batteries and discharge your batteries in a very smart way. So all these things take room. Again, if you have an off-grid system and batteries for backups, what happens when your batteries get full and you don't have any extra devices you need to turn on? You have to do something with that energy, and those are referred to either as diversion or dump loads. And most systems will have some sort of data monitoring equipment so we can find out how well it's functioning and what the performance has been like. So a couple things we need to think about it. So these are all the things that might need to fit in there. What is there? Where are they going? How much room do we need? Well, the working width of the space shall be 30 inches or the width of the equipment, whatever is greater. So if the equipment's only 16 inches wide, you still need 30 inches. If the equipment is 42 inches wide, you need 42 inches. Okay? The doors and the panels must be able to be opened at least 90 degrees. Okay? And we can't store things in the space where they're at with some limitations. And let me show you here. So this is an example of the equipment that we have. So here we've got an 18-inch wide piece of equipment. It needs 30 inches in the front. Notice we've slid it all the way to the left. Now I'm going to put this 18-inch piece here. I'm going to center that in the center. And then here's another. And so we're going to need a minimum of 30, 60, 90 inches to fit these 18, 36, 54 inches of stuff. So quite a bit of extra space. And remember, a couple things have to happen here. We have to be able to open the doors in front of them as well. Now, a working space can overlap the working space of other equipment. Now, this is per the NEC of 2008, which did not change in 11 or 14, so the slide is still valid. This is an example of do-it-yourself stuff, kind of funny looking things, you know, the way people have got everything plugged in here. This is a little ugly. I'd say not a good connection. Not a good connection at all, okay? So, per the National Electric Code, the depth of the working equipment, if the voltage is in, the voltage to ground is 150 volts or less, and we have some exposed live parts on one side of the working space and no live or ungrounded parts on the other side, then we can get away with 3 feet. Okay, so you'll notice anything under 150 volts, 3 feet is the minimum distance that we need. But when we start getting to higher voltages, which we will in many cases, if we're putting in a big turbine, then once we get to condition 2, which tells us that there are live parts on one side of the space and grounded on the other side, or live parts on both sides of the space, you can see that we have increasing distances required. The height of the shop should be 6.5 feet. Okay? Existing homes, service equipment not exceeding 200 amps are permitted to be in spaces less than 6.5 feet tall, not exceeding a 200 amp service. Okay? So that's the kicker there, right? Will your turbine increase the amperage rating to over 200 amps? It's so long. If it does, then you would need to increase the size of your service connection. It would need to go to the next greater size, which is 320 amps. All right. So once you get existing homes, right? If you have a basement that's only got a 6-foot ceiling, well, you don't really want to have to raise the whole basement in order to do this. So this has been grandfathered in, but you wouldn't be able to do that in a new home. All right. So other equipment located above or below shall not be permitted to extend more than 6 inches beyond the front of the installed electrical cabinet. Okay, so it can't stick out towards the front. Meters will be installed in sockets, can extend beyond 6 inches of other equipment, but nothing else can. It needs to be enclosed. All right, so here's the height of the working space. We can see the 6.5 inch, right? That's fine. And now we're going to see we've got a 12-inch wireway, and it extends no more than 6 inches into the panel board's working space. Well, okay, so that's over here on this side. So this is okay, right? Both sides here, those are fine. But the transformer, it sticks out too far. So that's going to be a violation there. So your installer is going to have a lot more to do with this. So you will need to take pictures for your report, and you'll see some examples of that here in just a few moments. So we have to have this dedicated floor space, dedicated equipment space, and it's going to be equal to the width and depth of the equipment. Notice when we're using the word shall. Shall means it's coming right out of the code, and that means no, you have to do it. No arguing. Okay? Shall extend from the floor to a height of 6 feet above the equipment. Okay? And it says that there are no piping or ducts allowed in this dedicated space. All right. So this is an example of a dedicated space. This is a room, might be in a barn, not sure where it is. And if there's, in this case here, this was okay because there's the house panel and there's nothing that can be in front here. There's nothing that can be in front of this working space. But once you get outside this zone, now I can store some things over here, right? Now this air compressor, on the other hand, I don't know if you can tell here, but this panel extends below the bottom of this air compressor. You can't even get the door open all the way. Definitely a fail. Fuses, circuit breakers, and other overcurrent devices shall be readily accessible, meaning you don't have, if you have to step up on a ladder or crawl up around something, that's not readily accessible. It's going to be installed so the center grip of the operating handle, when at its highest position, is not more than 6 feet 7 inches above the floor. Interesting number. Wonder how they got that. My mom couldn't reach it. I could, though. It's not allowed to be put in a closet, over risers of a stairway, or in bathrooms. So these are areas that we had seen them installed in, and it's no longer allowed. So the BOS, where are you going to put it? We need to say where we're going to put it. We need to take photographs of where we would recommend that it get installed, and those photographs then we will illustrate using a couple of, here are some examples of things we could use. Google has a program called SketchUp, Microsoft has Paint, Adobe has Illustrator and also Photoshop. There are many, many others, and in this course we are going to have some demonstrations on how to use several of these. And so we'll have to make some of those drawings. So for example here, so this is a photograph of where we thought, hey, we can put it in here. Now right now you can see there's a box stored on the floor. Not good, that's got to get moved out. Okay, where it says 7 feet here, you can see how there's an arrow going up while the arrow going down somehow is missing, right? So this is a 7-foot ceiling. We're going to put a board on the wall, and on that board we'll mount the inverter and the disconnect. We can see the service panel over here, and we can see that this is also where in the basement where the pump is. So this is actually okay. This would work right here, so long as we have our spacing as noted by the NEC. So in the report, we have to put down what the amperage is. We have to put down who the service panel manufacturer was. Is it square D? Is it a model QO? Is it what model is it? What is the voltage in phase, single or three-phase? Are there any empty spaces? The feeder panel, it could be that we have a main circuit disconnect and then it feeds into a feeder panel. So that's why it says if applicable. If you don't have a feeder panel that feeds off of the main panel, then you can skip that part. Area available for the balance of the system. We can see the length, the width, and the height. And then we need to describe the spot, the basement, the garage, the this, the that. We have to tell exactly where it's going to go. Now, there are some advantages of being on the grid. And one of these is that you don't have to mess around with batteries. The grid becomes your batteries. So if you're making more energy than you're using, it goes onto the grid, and your utility company keeps track of how much money you've exported to the grid, subtract that from the amount of energy that you purchase from the grid, and then you put it back in. So we need to spell this out in the report. Again, the customer may not have a clear understanding of why they're doing this or how it works. The other advantage here is if instead I was off-grid and something was wrong with my turbine, I would be left in the dark. So by having the backup grid there, well, that's a good thing. The grid-connected systems that don't have batteries operate more efficiently than the ones that do require batteries. And then also, because if we're putting it on the grid, it's possible that if I am making more energy than I'm using, that I could have it's possible that I could gain some revenue, although that's happening less and less. Disadvantages. What you may not realize is that if the grid goes down, so does your turbine. Shuts right off. And that's because of the anti-islanding rule required by the UL Rule 1741. But there are some new inverters that work in the PV world that have some built-in backup outlets, just a couple, that maybe you could put the refrigerator on, or the pump, or the sump pump, something that is critical. And so you don't necessarily have to have a huge battery bank, and it'll last for a little while. But other disadvantages here, disadvantages of interconnection. The grid goes down, you do too. When you have a battery backup, they're less efficient and that they cost more, and then there's more maintenance and replacement costs. Those are some of the off-grid problems. If I'm connected to the grid, I will pay additional meter fees, more than likely. It's possible that there will be some resistance from the utility that they will not want to have net metering. They will not want to pay me the retail rate for my electricity. There will be some paperwork and hassle involved, and believe me, it's not very fun. This is pretty cool here. I think we've probably all seen this. The Simpsons got a wind turbine and they're trying to get it to spin, and I think they forgot the second law of thermodynamics, that we can't make it spin with electricity caused by the turbine that we're using to make spin. Look, they even plugged it into it. Pretty funny stuff. We read a little bit about this before in our chapter here. We know about PURPA, the Public Utilities Regulatory Act, which allowed people to get connection to the grid and have renewable energy equipment. It references avoided costs, which means the amount of money or the wholesale rate that it costs the IOUs to generate their electricity. The Federal Energy Regulatory Commission, FERC, ruled in 2001 that excess generation is a credit, not a sale. Okay, so renewable energy systems are not power plants. We're merely being credited for the energy we're using and those few times when we're using more than we're buying, or when we're making more than we're using. So net metering, we'll just read this verbatim here, a system of utility interconnection that it credits a home renewable energy system for kilowatt hours generated at the same rate the utility charges up to the home's level of usage. Okay, so again, if we look back here, if during the month of June I only used 484 kilowatt hours, that would have a value if we use 10 cents per kilowatt hour, so it's $48 worth of electricity, right? $48.10. It was 10 cents per kilowatt hour. We can see mine was a little bit higher than that. I think I was paying closer to 13 cents a kilowatt hour. Okay, so if my system generates the same 484 kilowatt hours, once I start generating more, it's not like they're going to pay me back for this, right? They're going to just start crediting it, because maybe next month in July, when I make 500 kilowatt hours worth of electrical energy, notice here that I still use 658. So when I subtract one from the other, I will still be charged for 158 kilowatt hours worth of energy. So this is how the math is done on these. The credits are either going to true up each month, or they will get rolled over and get trued up annually. Okay? Annually seems to be the more popular way for the utilities to do it. Chris gave us a pretty nice drawing here. So we've got the turbine itself, which then is going to feed the inverter. The inverter will feed either or both the load, and if there's excess energy, then we're going to feed back to the grid. The grid also will feed the loads. We've talked about this in previous chapters about the database of state incentives for renewable energy and efficiency. So that's this right here. We can look by state and see what they are. DSIREUSA.org right here. We can see that there. Okay, and they change, and they also list those that historically maybe have already expired. So you can see what used to be and what is. So that is it for this particular module. So we've done modules 2. Module 3 follows also. And we can see the references that are listed here. I believe there might be a couple here that are expired, but you could maybe look at some of those too. But I've updated the ones that are correct. So